Last time we talked about Newton's method and we solved the problem in two different ways. The first one is a one-dimensional problem. So inside the one-dimensional Newton's method, you will calculate the first order derivative and the second order derivative. Then we talk about the two-dimensional Newton's method. Actually, it's good for multi-dimensional, any number of variables. And in the multi-dimensional method, you need to calculate gradient. Gradient is a vector that is composed of all the partial derivatives. And you need to compute the Hessian, a huge matrix. Inside the matrix, you need to compute for the second order partial derivatives. Okay, so today we are going to talk about a different method called steepest descent. There is a reason why people sometimes use steepest descent. The main reason is because Newton's method can be computationally costly. If you take a look at Newton's method, when you try to compute for the Hessian, there are a lot of terms, okay? And nowadays, people use computer to evaluate derivatives. Or in real life, you still need to find a way to compute for derivatives. So when you know the function form, it's easy to do derivatives, but sometimes you don't know the function form. What does it mean? So knowing the function form is like, there's a function looks like this. Okay, you know the mathematical equation of it. Then when you take derivatives, it's very easy. You can do it right away. You can do second order derivatives. You know the equation. You know how to do it. But in reality, sometimes you don't know the function form. Let's say you are having a car design and you are trying to figure out what's the performance of the speed with respect to the some design parameter, for example, the size of your bolt. Or they're somehow indirectly related. If you try to drive a car and you want to speed up the speed, maybe you need to enlarge the power, and then your car may be size-wise, you may need to buy bigger components, heavier components. Then you may need different sizes of bolts. Okay, so somehow there are some indirect relationship between some parameter and some of the performance. If you try to derive the math equation of that function and particular variable, sometimes it's difficult, okay? Or let's say another example about car. You want to design, for example, thickness of the metal plate inside the car. And you want to crash the car into the wall and you want to see how much deformation it's gonna make. And the thicker wall you have, the stronger car you will have. And then when you crash your car into the wall, fewer deformation, right? So, but of course, you will have a too heavy car, too bulky. So you know what you want. You know thicker dimension makes your car stronger. So when you crash into something, you have fewer deformation. But again, it's hard to determine the function equation between crash deformation and the thickness of the wall. One way to find out is to crash it, okay? But when you try to take derivatives, something like this, or one of the variable, when you try to do that, it's like xi is one of the particular dimension you are interested, and f is some particular function that you are trying to study. Now you don't know the function form, so if you make an initial guess and crash the car into the wall, then it's like you know the function value at certain position of the x. So it's like this. You evaluate the function. So it's like you can do one experiment for it or one simulation for it. Then you know the result. So how can we use experiment sampling to determine partial derivatives? You can use the so-called finite difference. So by finite difference, your partial derivatives is close to, by the definition of calculus or definition of derivatives, is close to I should actually I shouldn't put an I here because multi-dimensional. It's like this, right? Your x is a vector. K represent k value. So it's like by finite difference, what you can do is you can have a small increment on xi minus the function value at k divided by the small increment. This is basically the definition of derivative. Okay? This is your kth design. You want to do partial derivative with respect to xi. So you only have small increment on the ith coordinate. So ei, remember, is a normal basis. Ei equals to the component, the ith component equals to 1, the other are 0. So this means you only have small increment on ith component. Okay? So let me show you one example. Let's say your xk is a vector, for example, 2, 3, 4. Let's say it's a 3-dimensional problem, and you have specific function, right? And you want to know what would be the partial derivative of with respect to xi. And let's say you want to study the partial derivative with respect to x2 at the current design. Something like that. So what you are going to do basically is you want to plug in your function value at the current design, but you want to have a small increment on the second variable minus the current one divided by this delta. So that's how you can numerically estimate the partial derivative. It's not accurate, but at least you can compute for the derivative even though you don't know the function form. So in reality, in many cases, we actually estimate derivative by finite difference. even in computers. Okay? Do you think computer really understand the function form? Maybe not. The computer only just take a small increment on the ith component and evaluate again. Okay? So if I show you let me see how I can show you. I cannot show you here. In the future, when I introduce a different method, then I can show you MATLAB is actually also using finite difference. Okay, so this is a so-called a forward scheme. What does it mean by forward? It's like you take one step further in the step size of delta. Is this the only equation? No, you can have a backward scheme, you can have central scheme. So sometimes I make a drawing of this. This is along the direction of xi, and this is the position of your xk. And along this xi direction, you take one step further. So the distance is delta. Okay, so forward scheme is like you evaluate the function value here minus the function value here, then divided by the step size. If you want to do backward scheme, I use green color. So if you do backward scheme, you use the function value here minus the function value in the back. So over here, you take a decrement of delta. So you use function value here minus function value here divided by delta. Again, that's also estimation of the first order derivative. And what is a central scheme? So sometimes people will take half of the delta forward and backward. So half of the delta forward and half of the delta backward. Use function value here minus here divided by delta. Okay? All three values may be different if the function is nonlinear, but they will be close to each other when you have small delta. Okay? I like to use forward scheme, and I can tell you why. When we are trying to work on optimization, we care about one thing, so-called the function call. What does that mean? It's like a number of times you evaluate the function. Okay? Oh, by the way, whenever I do this, that means number of. Okay? So it's a more efficient way to make notes. So let's say it's like a number of experiments you perform to find optimization results. So over here, how many times we evaluate the function? This is one time. We plug in this design variable. This is the second time. We make a small increment on the second variable, and then we plug in the function again. Let's say whenever you plug in the function, you need to spend $1. So for this value, I spend $2. So controlling the number of function calls is like controlling your budget. In reality, when you are in a company, when you are doing optimization, nothing is for free. You need to have a design and test. Then you get one function value. You change a little bit, perform experiment again, That's the second function value. So it's like a number of times of your function evaluation. So when I work on research papers of optimization, actually people are deriving new methods for fewer number of function calls. You can develop a new method, but if the function call is 10 times larger than the traditional method, then why bother introduce a new one, but actually more costly? Okay, usually people try to develop new methods which are occupying fewer number of function calls. Okay, so actually if you are working optimization, if you can find a new method that reduced the required function call, that's a good development. Okay, so now I want to explain to you why I work on forward scheme. Because at the beginning, you definitely need to know the function value at the current position, right here. So if you can only spend one more function call, then you can get the first order derivative. Then I will not use central scheme, because if I use central scheme, I need to evaluate the function 2 more times. I need to evaluate at the red x, the two crosses. That means I need to spend 2 more times of function calls. Okay, so that's why I will choose forward scheme. Now let's take a look at the second order derivative. So if I want to do this is second order derivative. So I'm not going to prove it. I'm just going to tell you what's the result. I think you have learned this in calculus. So the result is actually this. You have your small increment on the ith dimension minus 2 times the function value at the current position plus the function value at minus ei divided by delta squared. So over here you can see when you are doing second order derivative using finite difference, you need 3 positions for your function values. So here is delta, here is delta. Okay? So this one is right here, the function value right here, minus 2 times of the function value at the current point, plus the function value in the back. So in, for example, Newton's method, when we did first order partial derivative, we already computed for f and also the one with plus delta. So we don't need to evaluate again. When we want to evaluate for the second order derivative, this is the only value that we don't know. So function call management actually is important in computing, because you can save a little bit of time. Okay, and my students are working on real-time optimization for collision avoidance. A robot is moving and it could be bumping into something. So the robot may have 1 second to take reaction. And inside his computer codes, he needs to evaluate certain function maybe 300 times. So the 300 times is the amount of function calls required to find out what's a safer trajectory. And he is already managing the number of function calls in such a way. So whenever there's a required calculation, if you in computers, like in computers, if you are calculating for this first order partial derivative and second order partial derivative, you compute for this guy and this guy. Okay, that means you already evaluate the function value once here, another time here, so that's twice. And when the computer code move on to the next line and trying to evaluate for the second order partial derivative, if you are not managing well, you may evaluate all three functions once again. That's 2 plus 3, right? But if you know you have done that already, fxk, you have did that already, and you have done the x plus delta already. So only thing missing is x minus delta. So you only need to compute for the third time. So that's how my student was able to perform real-time calculation to determine whether a robot may hit into something. Okay? So this is for second order partial derivative. But how about second order partial derivative with respect to two different x? So those are the off-diagonal terms inside the Hessian matrix. So how about this one? Okay, so I'm gonna tell you how it's looking like. So it's a little bit more complex. Okay. Writing it down makes you scared. Oh, it's such a long equation. But if I make a drawing of it, then you will know what's happening. So this is the xi direction. This is the xj direction. Here is your xk. And you are having delta increment on two directions. One is along the ith direction, the other one is along the jth direction. So you will be using 4 different positions for your function values. So this one minus this one and minus this one plus the original one. So whenever you are estimating the second order partial derivative with respect to xi and xj, you can do this. This is forward skip. And from here you can see these two has been used when we did partial derivative with respect to xi. And these two has been used when we did partial derivative with respect to xj. Because we obviously have to go through all the index. So I goes from 1 to the last one. So these two, any two, will be evaluated. So you have these two when we did the forward scheme for xi, and you have this two when we did the forward scheme for xj, but you don't have this one. This is called it's like an off-diagonal, or I call them off-diagonal terms. So you need to have increment of delta along I and also along j. So you are going to make a function evaluation right here. So this is what's happening. So if you cannot understand this, let me show you one example. So if your xk is 1, 2, 3, 4, 5, and if you want to know a function value at delta E2 plus delta E5, what does that mean? That means you are doing this. You have a delta increment and a delta increment like here. Okay? So that's what's happening in computers. Okay, so after understanding doing partial derivatives in computers could be time consuming. So if you can avoid, in Newton's method, if you can avoid Hessian, remember we need to, here, this is Newton's method. Remember this guy, Hessian? Hessian is a matrix that is composed of all the second order partial derivative terms. There are many of them. So if you are using finite difference, you will need to do a lot of function evaluations for this matrix in that iteration only. So that's could be time consuming. Okay, so in today I will introduce a different method which is trying to avoid using Hessian. Okay, now it's a method called steepest descent. Okay, this is actually the method that is well used in AI right now. So right now we have AI is based on neural network. It's like a bunch of neurons. Now you probably have seen some of the information of the neurons. So in each neuron, there's a bunch of values coming in, doing some math, and then values going out, right? But each neuron has a lot of unknown parameters. If you study neural network in the past, inside there are a lot of W's, weighting coefficients. So each neuron may have 10 or even more weighting coefficients. And let's say you have 1 million neurons, then you may have 10 million, 100 million unknown coefficients, W's. So think of neural network as a super high order polynomial fit. You can think of AI as something like that. So what is a polynomial fit? So it's like curve fitting or polynomial fit. It's like this. You have a y or f function equals to summation of I x order of I goes from 0 to n, something like this. So basically, it's like a an xn plus an minus 1 xn minus 1 da da da. So if you try to write down the math equation inside the neural network, at the end it turns out it's something like this, but way more nonlinear. This is a linear equation. Actually nonlinear. You have multiple terms multiplying with each other. But in this case, only one variable, one x. But neural network is multi-dimensional, multi-coefficient. So when you try to do curve fit, these are the unknown parameters. So what does curve fit do? Or regression. People use different terms. You know linear regression, right? If the equation is linear, then linear regression. You try to figure out what's the linear equation that best fit the trend of certain function, right? And this is nonlinear regression or curve fit, polynomial fit. So in neural network, you try to estimate what's the best function that describe the relationship between some input and some output. But in neural network, it doesn't directly tell you the function form. But in fact, behind a neural network, it's a function. A very, very super complex function. So what's happening when you train AI? You tell the AI neural network, you tell AI certain input and ask the AI to meet certain output. So usually the training data is a lot. It's like a list of required input and matching output. So it's just like what you're doing in linear regression. You are sampling, you are giving the data for fitting. So in curve fit, you will try to solve a problem. It's like an error of your estimation. So error of your estimation can be described as the true function minus the estimated function, right? And if you can minimize it, then then you can find the best fitting function. So what's happening is, even in neural network, when you plug in a bunch of input and output, it will use an optimization method to solve this problem. It will try to find the best fitting coefficients so that the neural network model that you determine at the end will have the best fit for your plug-in input and output. And basically it's doing minimizing the error of your estimation. And what are the variables? Those are unknown parameters. Okay? And nowadays, since the neural network is so big, so there are thousands of unknown coefficients, like those an and an minus 1. They're way too many. So if you think of this function as the function that AI is trying to solve, if it's using Newton's method, it's doable. But in that case, the AI training process requires evaluation of the Hessian. So for AI, there's always an initial guess, and then you will perform finite difference for the gradient and second order derivatives. So Newton's method will tell AI what's the next design variable, and then iteratively, eventually you can get a solution, but too costly. So nowadays, AI doesn't want to perform second order derivative, only first order. So what AI is doing is actually this method, so-called steepest descent. Okay? So what does the steepest descent equation look like? So steepest descent. Wrong. Minus. So only difference between Newton's method and this steepest descent is that no longer evaluating Hessian's matrix. Okay? Instead, steepest descent method introduced something called alpha, or people call it step size, or many other names. One key for steepest descent is that it's trying to move along this direction, minus gradient direction. So if I make a drawing, if I try to show you a function, here is x and here is y, and if I have, this is my gradient direction, right? So in this particular drawing, my gradient is positive, which means if I move forward, function value increases. So I have positive gradient. If I do that, if I move along the positive gradient direction, my function value will increase. So I should move backward. I should move along the negative gradient direction. So I know my function value can drop. That's why we want to move along the negative gradient direction. Okay? We move along negative gradient direction, so I can make sure if I move along that direction, the function value drops. So I can minimize the function. The only thing is how big is the step. So alpha k right here, step size, is a scalar, not a vector. It's a scalar. And it has to be positive. If I have negative alpha, that means I am not improving. I am not making the function value dropping. If I have negative alpha, I will be moving up. Okay, so in the future, when you use this method to solve any problem, or in the exam, or in your project, or anywhere in the future, when you see negative alpha, you did something wrong. Okay, you need to be sure of that. Okay? So, the key is how to determine step size. Okay? Now I would like to make a drawing of a 2D like a contour view, okay, from the top. In the past, we have seen how I did it in the MATLAB. Now I want to make a hand drawing of a specific some problem like this, and let's say my optimal solution is right there, and let's say my objective function contour looks like this. Okay, so here is higher f, and here would be lower, right? So you know, if I go along this direction, go inside, my function value drops, right? So whenever you take derivatives or gradients, you actually will end up with vectors that are perpendicular to the contour. Contours are curves with same function values. And if you take gradient or derivatives, that gradient vector is always perpendicular to the contour. Okay? If you want the proof, I can show you. For example, if I have f of x equals to x1 squared plus 10x2 squared. Okay, and then the gradient vector would look like this. It's like a 2x1 plus 20x2, right? And if I plug in a location, for example, 1 and 1, then it's gonna look like 2 and 20. Okay? So if I make a drawing of this function, x1 and x2, it's gonna look like this. It's like an ellipse, right? And here is, for example, position of 1 and 1, and the gradient will look like this. So this vector is gonna be 2 and 20. Okay? If I try a different value, for example, 10 and 0, 10 and 0 is right here. So I will have 20 and 0, so it's going right. Or anyway, basically they are perpendicular to your contour. Okay? So if I made an initial guess, for example, somewhere right here, if my initial guess is right here. So for example, this is my x0. So my gradient would be perpendicular to there. This is my gradient at k equals to 0. So I need to move along the negative direction. Okay, so this is my negative gradient direction. So along this line, where is the position with lowest function value? I'm sorry. So this is like a function value level 3, level 2, level 1.5, level 2 again, level 3. So it's somewhere here, right? So I want to find the lowest point along this line. So that would be my next design position. And then I will be doing this again. So this would be my desired x1. And if I do this again, here would be my gradient direction. And here would be my negative gradient direction. So then this would be my x2. So from this drawing, did you see that I will be doing some kind of zigzagging and getting closer to the optimum? Okay, so that's steepest descent. It's always doing this kind of zigzagging. If Taiwanese doesn't know, zigzag. So if you do this in English, it's called zigzag. Okay. Okay. Only question right now is, how do we know how much further we should step forward along this negative gradient direction? So that distance is very important. That's basically step size. we need to figure out alpha. Okay? So I'm going to draw a solution process and then tell you what we are going to do. This part is starting to be a little complex. So please be patient on this. Okay, the solution process. Okay. Now, initially, you have an initial gas. Right, this is your initial gas. And then you only need to evaluate for the gradient. You don't need to evaluate for Hessian anymore. Now the question is, how do you do this? I will use a different color. If I know alpha, then I will do the usual convergence check. A small number. The usual check, right? And if not converged, k equals to k plus 1. If converged, optimal is the latest solution, right? Everything is just like what happened last time. Only difference is that there is an unknown alpha. So in order to evaluate for this unknown alpha, we are actually going to solve a different problem for alpha. This procedure is called line search. So there is a line search. It's actually a subproblem. Okay? So in this subproblem, you are going to moving on to here. But right here, you will have different iterations. So I will use a different iteration symbol. So now I will use M. So this is a different iteration symbol. M equals to 0. And I should have an initial guess. But what I'm guessing, I am actually guessing the value of alpha. So over here, the value, the design variable becomes alpha. And I am having this initial guess of alpha. So alpha can be any value right here. But I know alpha has to be positive. So sometimes right here, I just pick up alpha equals to 0. Let's start from 0. 0 means no movement. And then let's try some mathematical process right here to find out what's the best alpha. Okay, so this is the initial stage. Okay? So right here in the subproblem, how I am solving this problem, I will actually use one-dimensional Newton. Why I'm using one-dimensional Newton's method? Because in this subproblem, there is only one variable, alpha. And it's an unconstrained optimization. And I know Newton's method can very effectively find the solution. So the subproblem is a Newton. It's only one-dimensional. So I don't really need to do Hessian. It's only F double prime. So over here, what's happening is you will be computing for F prime of alpha m and F double prime of alpha m. I will have more detailed explanation later on, but I'm just telling you what you need to compute right here. And then you need to do Newton's method here. So alpha m plus 1 equals to alpha m minus F double prime alpha m over F only one prime. F prime here, F double prime at the bottom. And then you will do your the convergence check. Alpha is just a scalar, so only absolute sign, absolute value sign. Is it smaller than some small value? Okay. A check. If not, go back to here. Then iteration number plus 1. If yes, update alpha. So your kth alpha equals to the optimal alpha on the subproblem, and that is your latest one. Okay? So the complete process is like this. How do I know the step size? I solve a 1D Newton's problem to find the optimal step size. Okay. Okay. In the drawing, let me explain how this is gonna look like in this drawing. So when you already know you're trying to find a solution along this negative alpha direction, and you know when you try to visualize the function, and like I said earlier, this is level 3, level 2, level 1.5, level 2, level 3. So it looks like a shape like this. It's like a convex function, right? So you are actually solving for unknown alpha along this particular 1D direction. That's why it's called a line search, along this line. And once you make a decision, okay, this is my starting point, and this is my moving direction. This point is being decided. This direction has been decided. Once you decided, you don't change it anymore. The only difference, only unknown that you're having along this line is how big is the step. So only unknown along this line is alpha. That's why in this subproblem, it's a 1D problem. Alpha is the one-dimensional unknown. So I know it's a little confusing. I will show you how it's gonna look like mathematically by one example. So let me just directly show you an example. Okay? So if you want, you can solve with me. Let's try to solve, minimize just some random problem, okay? And let's say our initial gas is something small, not too big, 2 and 2, okay? And I know my gradient f looks like 2x1 minus 5, 4x2. Okay, that's the function form of the gradient. So now I'm trying to solve this problem. I need to follow the steepest descent equation. So it's gonna be something like this, right? So this will be 2 and 2 minus alpha 0, some unknown alpha, and then 2 plug in. So 4 minus 5 minus 1 and 8. Okay? So I can put everything together. 2 minus 1 times of alpha 0, 2 minus 8 times of alpha 0. Okay? So x now becomes some function of alpha. It's actually a function of alpha, right? So if I, this is my f of x, right? If I plug this whole thing back to the original problem, originally we are minimizing f of x. Now I plug in f of x1. Actually, it's a function of f of alpha 0. Now it's a function of alpha 0. I just plug in. So how do I plug in? Just plug in. So 2 minus alpha. Oh, my 2 and alpha looks very much like each other. So I will try to avoid confusion. Square plus 2 minus 8 alpha, 2 minus alpha. Okay? So now you see your function f is actually a function of alpha. So you are actually minimizing a function with respect to the unknown alpha. Okay, and this is where you will do your solve it by the subproblem. So here I'm starting with the subproblem. And I will have initial gas n equals to 0. And I have a initial gas, let's say 0. Okay? So in of course, I need to derive this f of alpha, but I'm very lazy. I just ask MATLAB. So 2 minus alpha square plus 2 times 2 minus 8 alpha square minus 5 times 2 minus alpha. Okay, MATLAB solve it for me. I didn't show you on the screen, sorry. So this would be 129 alpha squared minus 63 alpha plus 2. if you derive it. That's the alpha. Okay? So now, from here I know my f prime of alpha equals to this 258 alpha minus 63. F double prime of alpha is 258.
Professor,
Yeah,
there in the first line,
I made a mistake.
yeah, I
Wait.
think it should be 2 plus alpha 0. No, 2 minus alpha.
Oh yeah. Thank you. My mistake. So it's a plus. Plus. Okay. Thank you. Okay, so 129 negative 65. Okay, thank you. So slight difference. Minus. Yeah. Okay. Okay. So then just solve it like Newton's method. So alpha 1 equals to alpha 0 minus f prime of 0 over f double prime of 0. So you will have 0 minus negative 65 over 258. So that gives me 0.2519. Okay? And obviously, if you check the difference between the new one and the previous one, it's still larger than a small value, so not converged. So you move on, m equals to n plus 1, so now m equals to 1, so I need to do it again with m equals to 1. So here is alpha 1 minus this. So here would be 2519 minus 258 times 0.2519 minus 65, 258. Okay, and the solution is the value on top is very small, 0, 0, oops, 0098 over. Okay, so it's very close to the same solution. So from here you can tell Newton's method can find the solution actually in one iteration, but you still need one more iteration to confirm it. So it's very close to 0, converged. Okay? Now, my optimal solution, right here, what I was looking for is this. So in the subproblem, my optimal is 2519. So I will update back to main problem. Okay? So my main problem was here. Copy. My main problem had this, right? So now I just put the numbers back. So this is how you do it. Okay. You first start with one. You start with a gradient direction with an unknown step size. So everything becomes a function of alpha. You use a 1D Newton. By the way, you don't need to use 1D Newton here. You can use any method for the line search. I like to use 1D Newton because only 2 iterations I can get solution. So I use 1D Newton, and then I know the optimal alpha. I just plug back to here. That gives me the updated x for this iteration. Then you will continue with your convergence check and do this again and again. Okay? This method actually is not very effective because it's always doing this zigzagging movement, and it doesn't go toward the optimal right away. So it's doing this. I can show you how it's gonna look like in MATLAB. Okay. Before I move on to MATLAB, any questions?
This method apply for non-continuous function also.
Non-continuous, no, we can only solve for continuous function. Because if a problem is not derivable, not differentiable, then you cannot use gradient-based approach. You can only solve for differentiable problems. So obviously it has to be continuous and also smooth. Okay, you can have piecewise function connected, but right at this point, the derivative doesn't exist. So gradient-based approach cannot handle weird derivative somewhere. But numerically, sometimes we don't care. Because we cannot guarantee a real-world problem is always nicely continuous and smooth. Sometimes you do have piecewise connection. So unless you are super unlucky, your evaluation bump into that weird point. Otherwise, you're fine. So sometimes your searching goes from one side to the other side. The only difference is, only issue is sometimes when your solution process move from one region to another region, the slope gradually changed. So you may be jumping around by the gradient. Okay? Okay. Now let me move on to code. Okay, so this is the code from last time. This is the Newton's method code, and this is the multi-dimensional Newton's method. So I'm gonna do some modification of it, so it becomes a steepest descent. And if I run the code again, you can see how Newton's method was able to find the solution in one iteration. So boom, boom. Right there, right? And only 2 iterations. Newton's method was able to find a second order polynomial like this. Now we are moving on to this steepest descent. So I'm changing this to steepest descent. Okay, and I don't need Hessian anymore. I'll just get rid of it. Okay, no more Hessian. I will just get rid of the things I don't like. Oops. Okay, so right here, this is what we had earlier for Newton's method. We have x minus inverse of Hessian times gradient. Right? So we don't have Hessian anymore. So we need to define a new variable called alpha. I am going to use symbolic again, and I'm gonna use small case a to represent alpha. Okay, so I will also have. So here basically is gonna be my a. Oh, a. So if I pause right here, if I pause right there and run the code, you will see, I cannot do this because this is a symbolic. You cannot plus and minus right there. So, so maybe I will have a, I will do this later. I will just say, x but alpha. So x described in a function of alpha. So I will just define a new function just for that particular iteration. Okay, and then I will plug in the updated alpha later on once I have it. So I don't put alpha here. I will put I need a while loop here. So initially I will say m equals to 1, and I will use capitalized A to represent my the values of my alpha. So it's a one-dimensional value, so just capitalize A, bracket small m, initial guess equals to 0, like what I did in the note. And I need an error value, but for the subproblem, so I just have a underline A right here, something big, and a while loop, error A larger than 10 to the power of -3. And at the end, I have m equals to m plus 1. So right here, I need to perform Newton's method. So over here, how do I do Newton's method? You need to know the function. So you need to plug in. So right here, I will have a function of f, but in the dimension with a variable of a of alpha. So I call it fa. So basically substitute into f, replace x1 and x2 by the current x. The current x basically is the xa, right? So this is my current x, but with a unknown alpha. So I plug in here, so my f function will become a symbolic f. So fa is a symbolic f with an unknown symbolic alpha inside. So here I need to do derivative. I'm gonna call this df a equals to derivative of fa. My variable is a, and I plug in my current capitalized A. So this will be my f prime. So f double prime would be, I call it ddfa. I take the derivative again, and then no, sorry. Just this. It's this. Not yet plugging in, only derivatives. So in Newton's method, my next A alpha equals to the current alpha minus substitute dfa, variable A, and current A. Plug in the value. divided by the same thing, but DDFA. Maybe it will cost. I need to update the error. Error equals to the absolute value between these two, right? Minus. Let's pause right there. See what's. Let's pause here. Okay. So if I line 13. Okay, line 13. Let me see. This. Oh. Sub 2. I don't need to double it. Earlier we need to double it, but this time we don't. Let me see if it's doable. Okay, good. So from here you can see this is your xk plus 1 with unknown alpha. Okay, so this one works. Let's run again. Now your function of a looks like this. So this is plugging in the x of k plus 1 with unknown alpha. So this is your function with unknown alpha. So doing derivative right here, step, just one step, two step. So let's take a look at DFA. So this is first order derivative, DFA, second order derivative, okay? They are both symbolic, good. And then I should be able to do this. Can I? Yes. So this is after you plug in Newton's method. Current A alpha minus F prime over F double prime. Okay? But I think I need to double it. Do I? A is oh, I haven't run the code. I need to double it. Double this line because my A is double. Okay. So should be fine. Let's run the code. Okay. So at the end, my A is like this. Yeah, two iteration. One iteration I got 0.4815. Another iteration confirms the same solution. Okay, I end up with this solution. So now get back to the original line. Right here, I just plug in the latest solution. Just plug in here. So my m is 3. So just am. Plug in am. Okay, I don't need the debugger. Close. Plug in am. I don't think I need a second line. Okay? So let's take a look. Yes. This time I'm gonna make a drawing of the line so you can see the zigzag. When I plot, let me say x is equal. Yeah. X is equal means when you make a drawing, the spacing, the distance, the scale for the x coordinate and the y coordinate has to be the same scale. So right now it's not in the same scale. This is 5, but over here it's the 5 is this short. So this is kind of being squeezed. So if you say x is equal, you can have a same scale of drawing right here. After you plot something. You can say it right here. And whenever I make a drawing of the new point, I want to draw a red line from the new point, from the old point to the new point. So let me draw a line right here. So again, plot, but red line, so dash R. No marker, no need marker. But line width, maybe 2. Okay. So here, I create a bracket, and this is previous point, and here, previous point. Okay. So you should be able. Yep. So this is what happened. If I zoom in, you can see initially it goes down, following this negative gradient direction, and then if I zoom in more, you can see how this is always, how the steepest descent is always making this zigzag movement, and actually the new movement and the previous movement are perpendicular to each other. If I zoom in more right here, if I zoom in more, if I zoom in more, zoom in more. Okay, I think this is where it stopped. When the error between these two are very small, no more movement. Okay, so it actually took steepest descent 6 iterations to find the solution. So compared to Newton's method, let's open up Newton's method. Where's Newton's? That's right. Let's open the code from last time. So this is last time. If I also do the axes equal, and also draw the line, the red line. Okay. So this is Newton's method. Newton's method used inverse Hessian to figure out what is the best direction and also best step size. So Newton's method was able to reach toward the optimal in one shot. Okay, no more zigzagging. But if you use steepest descent, it's like this. Okay? So why bother use steepest descent? Because when the number of variables are large, the Hessian matrix becomes so large. It's like an n by n matrix. You need to perform the inverse of a n by n matrix. Maybe you have 100 variables. It's gonna be a 100 by 100 matrix inverse. It's huge. And also, think about this 100 by 100 matrix. Inside, you have so many second order derivative terms. And if you perform finite difference, you need to spend a lot of function calls. Okay. So, so people tend to use steepest descent. It doesn't require Asian. Okay. Do you have any questions? Okay. Now I will show you how to do finite difference in MATLAB code. Let me show you. So over here, everything is symbolic, so I can just use MATLAB function to do derivatives. It's very convenient, but in reality, sometimes you don't know the function form, so you cannot perform symbolic. So over here, I will create a different file. I think I will do finite difference in Newton's method. So you will get the code for finite difference with second order derivatives. So let me copy it here. This is with finite difference. Okay. Okay, so for finite difference, I can, in MATLAB coding, I can still do symbolic. The only thing is I don't perform DIFF. So overall, I will need a parameter called delta. And my delta would be something small, 10 to the power of -5, something like that. Okay, that's my small increment. So over here, sorry, I will need no, function value substitute. Okay, I will need f. I will call it FV, the F value. So substitute F and then here x1, x2, these. Okay, so the value at the current design, I will just use underline V to represent the function value at current position. So I will need function value with increment along x. I will just use underline x. Maybe I will say px, positive x. So it's gonna be like doing this, but I will have a small increment of delta times a vector, or just this, delta and 0. So it's an increment of delta at x. And then I will need negative x. So nx. So here is negative. I will do the same thing for y. So positive y, negative y. Here, basically 0 delta, 0 delta. And I will need positive x and positive y for the off-diagonal term. So it's gonna be positive here and delta delta, both with increment of delta. Sorry. So in this particular iteration, I will be evaluating f for 6 times. This is all I need for this iteration. No, I just need to assemble them in a certain way so I can get G and H. So my I can just write down whole thing inside here. So my G would be divided by delta, right? So something minus something. So this guy minus this guy. So that would be my first term. And then for the y term here is positive y. So that's my gradient. How about Haitian? Haitian, here divided by delta square. So I will have positive x minus 2 times current 1 plus the negative 1. Negative 1. So that will be my first term. And then I will use a comma to represent moving toward right of the matrix. But here I will have, how do you call this? Not column. What's the English name of this? The dot and the comma. Anyway, I forget. So for the last term, should be y. Right? And these two will be the off-diagonal terms. Off-diagonal terms, I will need this guy minus the positive, both of the positive ones, px and py, plus the original one, so here. Both off-diagonal terms are the same. That gives me Haitian. The rest are the same. I don't need anything else. I don't need this. So let's try to solve it. Boom. How about a very inaccurate delta? Let's say 0.1. So my gradient would be slightly inaccurate. Still, you get a solution right away. Because the problem is too simple. Maybe I try to make it more nonlinear, so it won't be so easy on solving. So let me try to make it the fourth order. And if I open up the original one, let's try to solve the fourth order. So x2 now is to the fourth order with symbolic. Let's take a look at the process. It took Newton's method 20 iterations to find the solution because of the super high nonlinearity. Okay, but Newton's method was able to find it with accurate estimation, quite accurate estimation of the derivatives, and it requires 20 iterations. So let's solve the same problem with finite difference, but here your delta is quite poor, the pretty big delta, and let's see how much iteration it needs. 15 times, how come? How come faster? How about delta equals to 1? Super poor. The solution is wrong. The true solution should be (2.5) and 0, right? But now if I have a pretty poor delta 0.1, you can see that it's a 2.45 and negative 0.05. It's not close to the solution. Still converged. And it was able to converge just because our termination criteria, it was not able to find a more accurate result and stopped. But we were just lucky that it stopped at 15th iteration. So let's say if I have pretty nice, pretty accurate estimation of the gradient, let's say delta is 10 to the power of -5. 20 iteration, 2.5, 0.0014. So with good good choice of delta, pretty small delta, your gradient would be more precisely estimated. So your gradient and your Hessian are more accurate. But this problem is very nonlinear. It's a fourth order in X2. So it took Newton's method to get to this point with 20 iterations. Let's see how steepest descent can handle this with a power with the order of 4. So let's open up steepest descent and power of 4, right? Here is steepest descent with symbolic. It's quite fast. Oh, maybe we're just lucky. Yeah. So sometimes steepest descent is lucky. Let me change to a different position. No. I need to figure out why steepest descent is doing so well. Why is that? Because of the I don't know why. It's not bad. But of course, it's not super accurate. It's not bad. It surprised me that how well steepest descent was able to find the solution. Okay, let me try 8 and 5 here. By Newton's method. Newton's method is very accurate. Is the x2 is 0.0015. It's very close to 0. But if you use steepest descent, y is 0.029. X2 is not as accurate. But I'm quite surprised that steepest descent was able to. But if you take a look at the moving direction, by Newton's method, it tends to go this way and then bump into this trap. This trap is because we have fourth order on the x2. So if you stay on this line, it's gonna be taking so much time to move along this very nonlinear x2 direction. But steepest descent, because of the behavior of line search, it moves toward this line so effectively and ends up with somewhere here. Maybe the line search took a lot of time. We didn't plot out the line search. So inside let me see how much time it did for the line search. So here is a steepest descent. If I just display the M, then we will know. Okay, so let me just display M. Okay, let's do it again. So for the line search, steepest descent, so the effort was spent in line search. Like in the first iteration of steepest descent, it took 6 iterations to find the lowest point along this line, and here 9 iterations. So from the moving trajectory, it looks like it didn't spend too much effort, but inside each line, you actually perform multiple iterations of 1D Newton in order to find it. Okay, so the effort was in the subproblem. Okay, so it's still not for free. So you can actually try to compare which one is more costly. How do you compare that? Let's compare the one with finite difference. So I need to write a code about the finite difference for steepest descent. So let me do that. The steepest descent, and here with finite difference. So we can compare which one is more costly. Here I have Newton for finite difference. Here is steepest descent. Now I'm going to modify. I'm gonna copy some codes here for the gradient. So the gradient is here. Okay. So I have the gradient, and then inside the subproblem, I also need to evaluate derivative. So here, it's I need to compute for the function value. I can just do substitute here, but current A, yep, current A, but plus delta. So overall, I also have this delta outside here. So this is AM plus delta minus AM. This whole thing divided by delta. So actually, let me think. Yes, you do need this. And then, so maybe I should define call the FA value with positive delta, and FA value with negative delta. I need these. So let me write down in this way. So this is with positive delta. This is with positive delta here, and this is without increment of delta. And over here, I need one for negative. So positive delta minus the function value here. And the second order derivative can be derived by this, divided by delta squared, and here 2 times, and not 2 times, minus 2 times of this, plus the negative one. Okay, and I just need DFA over DDFA, right? Do I need double again? You don't need double anymore because everything should be. Oh, I think I still need double because they are symbolic. Okay, so let me try this. No. Py, where did I, line 17? Negative x, sorry. Typo. Poor performance. Delta needs to be smaller. How come? Does it need to be even smaller? Really? No, explode. Okay. It's too nonlinear for this. This problem is too nonlinear. How about here? Or is it too small? They made a mistake. Still solving. Where did I make a mistake? Let's try to solve a simple problem first. Okay, something is wrong with my finite difference here. I think I made a mistake somewhere. Let me see. Current A plus negative plus negative gradient plus negative delta. No. I did it wrong. Pick up the wrong one. Should be positive and y. Positive and y. So here should be positive and y. Yeah, that's the one. Okay. Now back to the fourth order. Yep. And then back to the problem 8 and 5. Yep, okay. You can see how it's following a different trajectory, but still, it was able to solve it. Let me try 10 to the power of negative 5. Okay, same amount of delta, same position, 8 and 5. Okay, and then what else? Okay, now we we need to count the function call. So initially you can say fc equals to 0. That's represent the function call. So whenever I evaluate the function call equals to function call plus 1. So this is the most precise way to compute for function calls. Whenever you evaluate the function call plus 1. So here you also evaluate the function call inside the subproblem. Okay, for steepest descent, for the outer loop, the main loop, you need 3 function calls for a 2D problem. So you can compute for the gradient. And for the inside loop, the subproblem, every time you will be computing for 3 function calls as well, because it's a one-dimensional second-order derivative. Also 3 function calls for one iteration inside the alpha line search. Okay? So whenever you do it, you will display every iteration you can display how much function call you made. So here, bracket function call equals to number to string function call. Okay, display. So you can see first iteration 18, 27, 54, 60, something, 99 function calls. So if you are solving a particular problem like this, and every time you perform a function call, it's like you are building something with certain design variable. This process means you need to build 99 of them. Okay? And if each of them require $1, you just spend $99 for finding the solution. How about Newton's method? Same problem. Here, function call plus 1. That's only places you evaluate the function. And outside, I'm gonna say function call equals to 0. And then I'm gonna display, same here, display the function call. Oops. No. Okay. So it was 99 for steepest descent. How about Newton? 120. Newton took 20 iterations, giving you a more precise solution, but 120 function calls. Steepest descent, fewer iteration in the main loop, but there are extra iteration in the subproblem, 99 function calls, slightly less accurate, is it? Actually pretty good. 0.008, pretty nice solution. So in this case, steepest descent is more efficient. 99 function call, Newton 120. Let's copy the solution. Let's do not clear the screen so you can see the difference. So this is a steepest descent. So I'm gonna run the Newton again. So from here you can compare. Steepest descent, 0.008. Newton, 0.001. So Newton is more accurate. 99 function calls for steepest descent, 120 for Newton. Same problem. These two different methods. Let's try. Earlier we had delta, pretty good delta, 10 to the power of negative 5. Let's try a poor one, like 0.1. Okay, this is final difference. And let's clear the screen, and then try to solve it again. It cannot be 0.1, too poor for steepest descent. So maybe 10 to the power of negative 2. Okay. So let's run the Newton. Okay, let's run the steepest descent. Okay, now compare. Newton's method, 16 iteration. Steepest descent, 8. This time Newton's method is more accurate and more effective. So it really depends. And for steepest descent this time, less accurate solution and took more function calls. So there's no guarantee for the method you use. They eventually find a solution, but numerically sometimes one method is better, sometimes the other is better. Okay? So that's actually everything I want to cover today. Next week, I'm gonna talk about steepest descent. No, conjugate gradient, another method. So let's take a look at our course schedule. Sorry. Today is 9th. Let me remind you, at the end of March, we will have exam. So you need to solve problems by hand using Newton's method, steepest descent, and also the method I introduced next week, conjugate gradient. Okay? So, any questions for today? Do you want to try a problem by hand? We have 1 more hour. I can solve it with you. Let's all pick up a note and then let's try to solve it. And then I will do it on the board. If you cannot do it, you can look at what I did, or you can just ask me questions. So we have 1 hour, I can solve it with you. Steepest descent probably is the most confusing method in the early stage of learning optimization, because it requires like a main stream of solving and a sub-solving stream. It's like switching from the main and the sub-problem. So it's a little confusing. Okay. We still have time, so let's try to solve the problem by hand. So you can do it in your notebook or whatever, and then you can take a look at what I'm doing. Okay. Did you try this already? We can try to solve this problem. I will try to continue on the next iteration. So everyone, if you want, you can try this one. Solve this particular problem. Try not to peek on my solution. See if you can get to this point. If you already did, I will continue on the problem. So I will write down the problem right here if you are starting from scratch. So the problem is like this. So if I say solve this until k equals to 3, that means initially k equals to 0. After all these, k equals to 1, So need to do another time k equals to 2, another timing k equals to 3. So that means if I say 3 here, you do this 3 times. Until or convergence. Or until convergence or k equals to 3, something like that. But usually in a problem, the problem needs to define what kind of convergence. So here I can say until the problem has to define properly. Okay, minimize this with this starting point using this method, solve until either this happen or this happen. So that would be a complete set of the problem description. Of course, in the exam sheet, I will describe this in more complete sentences. Okay. So let me try to solve this. I need my calculator. You can use calculator. Okay, so that would be the solution for first iteration. So you are supposed to solve this. So at 2.2519. So this is like you need to compute for the length of this. 0.119 square plus take a square root. So if you really do some calculation for this, you found that the difference between the current one and the previous one is not yet converging. So you move on to the next iteration, k equals to k plus 1 equals to 2. So you start with so this gives you 2.2519. Now, gradient. My gradient looks like this. like this. I just plug in. Okay. So your f of x2 plug in x1 squared plus 2 times squared minus 5 like this and continue. So from here you can see how much time it's gonna spend for you to solve using steepest descent. It's taking a lot of time. And meanwhile, you need to be very careful. If you made a small mistake somewhere, the rest will be incorrect. Okay? So in the exam, I will try not to give you a big number here. I probably will just ask you to solve for twice. I just want to confirm you know the process, and your solution won't be accurate, but because the problem will ask you to solve for only twice. At most 3 times, okay? And you know for a quadratic problem like this, if you solve with steepest descent, usually it requires 4 or 5 iterations to converge. In the exam, if I ask you to do these 4 or 5 times, it probably take 1 hour. With one small mistake, the whole thing is wrong. So I won't give you a hard time on doing this repeatedly more than 3 times. Okay, so I just want you to know how this is done. Okay? So if I continue, this will become a function of alpha, right? Then I go into the subproblem with m equals to 0, alpha m. Again, I have an initial guess of 0. So I know m plus 1 equals to alpha m minus f prime of m over f double prime of m. And then perform one-dimensional Newton iteratively. So at the end, you will get alpha star, right? And then update. You can get your second, the x at second iteration. I'm being lazy again. I don't want to solve it. Okay. Any questions for you guys? Do you want to just go? Okay, let's check on let's do a roll call. Okay. And let's see if anyone dropped the course. Oh, they dropped the course? Oh, okay, okay. So I can just get rid of them. Okay, so I need to do some regrouping, I think. So I think all I need to do is to move either Sao or Guoquan to the fourth group. Let's do this. 4. How about this? Okay. So now we have 2 students per group. Today is March 9th. Say again?
Oh, no, nothing.
Okay. Oh, so we have 3. That's fine. 3 for the first group. That's fine. So let's do a roll call. Yiquan. Okay. Giovanna. Okay. 志文。易安。Giuseppe. Okay. 子炫 yes. Facundo. Okay. 秋明 okay. 国宽 易涵 yes. Saul yes. Hong okay. 陈琦 安佑 okay. 明志 显义 okay. Louis no. You're Federico and 博源 okay. So do you guys know Louis?
Yeah.
Please remind him to come.
Okay.
Yeah. Okay.
Sure.
Okay. So I will recommend you to know your teammate today. So I guess we are pretty much settled for the grouping. And you can exchange your contact information. You can figure out what you want to work on. Try to know each other after the class. Okay, so I will leave this here so you know who your teammate is, and then you guys can talk with each other. Okay? That's it for today. Thank you.